So in this video, we're continuing the discussion of how we apply the ideas of integration to calculating properties of sort of physical objects. And in particular, we're continuing to focus on this sort of idea of going from some kind of distributed force to some kind of equivalent force. Right, you'll recall that in the last video, we started on that. And the way that we started on that was by asking the question, okay, how big is the equivalent force? And what we found when we thought about how big the equivalent force was that we achieved the size of the equivalent force by basically asking the question, what happens when we add up all of these forces? So we said the force equivalent, right, was simply the integral over the domain, right, whatever domain the force is being applied to. If it's a contact force, it's the integral over the surface. If it's a body force, it's the integral over the entire body of each little bit of force that's acting on each little chunk of the material. Okay, so that's conceptually what we're doing when we calculate the equivalent force. But if you think about it, that's only half of the question, right? Because when you ask the question, what's the equivalent force, there are actually two questions that you have to answer. One is, what's the vector? Right? But then the second question is, where's the vector? Because if you recall, when you apply a force to something, you're not only applying a force, you're also applying a moment. We need this equivalent force, the moment generated by this equivalent force, to be the same as the moment that is generated by the distributed force. Okay? So in this video, what we're focusing on is how do I figure out where the equivalent force is applied. So let's first start with the sort of simplest version of that, which is gravity. Right? Gravity is a body force, and the location that the equivalent force acts for gravity is at the center of mass. Right? So what is meant by the center of mass? Well, one way to think about the center of mass sort of conceptually is the center of mass is the sort of mass-weighted average position. What do I mean by that? Well, let me show you what I mean by that with first a sort of simple example. Let's say we've got a barbell, right? It has two masses on it. They're both equivalent, right? Well, the sort of average position of these two masses would be the position of this mass plus the position of this mass divided by 2. Since they're both the same mass, the mass weighting for those positions is the same, so the center of mass will be there at the center of the barbell, right? If I, on the other hand, had a barbell where one mass was small and the other mass was big, right? Then when I did the mass-weighted average of these positions, I would say, okay, well, I get some of this position, but I get a whole lot of this position, so maybe my center of mass ends up being more closely located to the larger mass, okay? Or conceptually, if I have a system that consists of 3 particles, right, that are all the same size, right? If they're distributed like that, my center of mass will be someplace in the middle. If I have 3 particles and one of them is much bigger than the other 2, my center of mass will be someplace located closer to the other one. So that's conceptually the idea of center of mass. And when we talk about that conceptually, one of the things you ought to be able to do is look at some object, right? So let's say you had an object that was shaped like this and ask the question, where is the center of mass of this object? And when you think about it, the center mass of this object, well, there's some symmetry here, so it's clearly going to be someplace on this center line. It looks to me like you're going to end up probably having the center mass someplace kind of in that vicinity. But you'd have to actually do the math to find out if that's right. So let's go on to talk about now how we do the math. So this is the concept, this is the mass-weighted average. Mathematically, we find the center of mass if we've got a system of particles by simply adding up the position of each particle times the mass of each particle, and then dividing by what the total mass of the system is. Okay, so conceptually, this expression is saying I've got this system that has some number of particles in it, particle number 1, 2, 3, 4, 5, right? I define some coordinate system. Here's my origin. I take the position of particle number 1, so this is R1, times particle 1's mass, position of particle 2 times particle 2's mass, position of particle 3. So I add all those up, right? That's doing a vector sum up top, and then I divide that by the total mass, right? Because I'm just adding mass 1 to mass 2 to mass 3 in order to figure out what the center of mass position is. Okay, so for example, if I had just two masses, right, one mass located at the position, say, 3 in the I hat direction, right? So there's one mass, and the second mass located at the position 3 plus 4 in the j hat direction, right? Maybe this mass has a mass of 1 kilogram, this mass has a mass of 2 kilograms, right? Where's the center of mass of that? Well, my center of mass position would be 2 kilograms times 3 I hat, right? Plus 1 kilogram times 3 I hat plus 4 j hat, all divided by 3 kilograms, right? And when I actually do that math, well, let's see, I get 6 I hat kilograms meters plus 3 I hat kilogram meters plus 4 j hat kilogram meters. I divide by 3, and so I end up getting 3 I hat plus 4 divided by 3. 4 divided by 3. Yeah, plus 4 over 3 j hat would be the center of mass. Sorry, I had a little brain fart there. So that's sort of a simple example of calculating center of mass for a system of particles.